And now, I want to return to an algorithm that we have seen a while ago, a couple of weeks ago, maybe even, maybe last week, that is secretly a recursive algorithm, although we did not think about it in that way at the time. So here is a familiar example, hopefully. Which is the Euclidean algorithm. So remember this Euclidean algorithm, we can use it to compute lots of different things. We introduced it as computing the greatest common divisor of two numbers, but you can also use it to compute Bezout coefficients and compute inverses to something mod m. But in this context, we're just going to talk about it as computing the GCD. So let's write down what this algorithm looks like. So I assume that we're getting inputs A and B, which are natural numbers, and A is greater than B. So the way this algorithm works, remember the Euclidean algorithm, basically you use the division theorem repeatedly. Etc. until you finally get zero remainder. And then when you get zero remainder, the thing you return was the last thing that was the remainder. So what this is saying is essentially that the end case for this algorithm is if b equals 0, then return a. So first of all, this is, you can think of this as saying that the GCD of anything with 0 is that thing. So GCD of a with 0 is always a. But also that's how you end the Euclidean algorithm, right? Is you find when you get a remainder of 0, and then you take the previous remainder as the output. Okay, so if b is 0, then return a. This is our base case, essentially. And otherwise, we use the division theorem to write a equals b times q plus r, whereas in the division theorem, r is the remainder, so it's between 0 and b. And then we return the GCD of b and r. So remember, from our discussions of the Euclidean algorithm, we know that the GCD of a and b is equal to the GCD of b and r. And also, just as a quick note, since we're requiring our inputs to be bigger one first, smaller one second, we know that r is smaller than b. So we are good to go calling the GCD algorithm on b comma r. So let's go ahead and do another run through of this, just to see how it compares to what we're used to using the Euclidean algorithm. So let's find the GCD of 53 and 25. So 25 equals 0, it does not. So we skip this step. And otherwise, we write, let's see, 53 equals 2 times 25 plus 3. This is our division theorem. And we will return the GCD of 25 and 3. So this is our first recursion. Again, we check if the second thing is 0. It is not. So so otherwise, since it is not, we write 25 equals 8 times 3 plus 1, I think. 3 times 8 is 24. And we return the GCD of 3 and 1. And then let me blaze through these last couple because it's going to be the same thing again, as you can probably predict. So the GCD of 3 and 1. So 1 is not 0. Skip that step. And the division theorem gives us a remainder is 0 now at this step. And now we have reached the base case. So we return whatever was the first argument, which in this case is 1. So this output is 1. And then you can see that unlike in the factorial, the reverse step was a little bit more complicated because we were adjusting it at each recursion and building it back up to get the result. But in this one, we don't adjust it at all. So we get 1 here as well, and 1 here as well. And the end result is that the output is 1. So the backward step on this one is much more straightforward. Once you've found the answer at the bottom, you just bring it all the way back up. And you can see that we're not writing it like this for extra clarity. We're writing it like this because we're trying to understand how recursive algorithms work. But you can see deep inside it is basically how you would do the Euclidean algorithm before, right? You would just use these lines. And writing it this way is basically just saying that secretly what you're doing is you're using a recursive algorithm to compute the GCD. So let's ask the same question that we asked for our factorial, which is what is the time complexity of the Euclidean algorithm? Or I'll just call it complexity sometimes. So we're going to need a little bit fancy tricks to figure this out, but you will not be surprised to find out that it has to do with recursion. So this time, instead of looking at the algorithm, like looking at the input and seeing how many steps it takes, we're going to work backwards. We're going to say it takes this many steps and figure out how big the input must have been to make it take that many steps. And at the end, we'll figure out what we're talking about. So let me let's start from the beginning. Let's start writing things down. So the first thing to note is that each recursion takes a fixed number of operations. So since we're forgetting about constants, we're just going to count the number of recursions. Because if we look in here, each recursion takes sort of one comparison and whatever amount of arithmetic it takes to do the division theorem, but it's just going to be, a couple of divisions. So by counting the number of recursions, we're essentially getting, up to a constant, we're getting the number of operations. So let's work backwards from where we did it before, and let's suppose that it takes n recursions to find the GCD. So if we write this out in traditional Euclidean algorithm style, that looks something like this. So A equals Q. I'm forgetting what numbers I wanted to use for these. Let's call this, what should we call this? R2 and R3. Okay. I think if I start from 2, I will match what's in the book, which is convenient in case anyone else looks at it. So for that reason, I'm just going to start from 2. They do that because they call this R1 and this R0. So I'm just going to call this R and start from R2. Okay, so the Euclidean algorithm starts out like this, with the division algorithm, and then we repeat, replacing A with B and B with R. So this is Q3 R2 plus R3, and then R2 equals Q4 R3 plus R4, da, da, da. And at the end, we get something like Rn minus 1 equals Qn plus 1 Rn plus 0. So no remainder on the last step. That is how we finish. Okay, and then the point is that we're going to look at these remainders and look at the relationship between these remainders. And we're going to think about that as a sort of recurrence relation. Because you can look at each of these steps as somehow writing one of the remainders in terms of others of the remainders. And in particular, you can see that each remainder depends on the next 2 in the sequence. So maybe that reminds you of Fibonacci numbers. So actually, we're going to compare them to the Fibonacci numbers. So how do we do that? So Rn is not 0, so it's at least 1. So it's greater than or equal to the second Fibonacci number, which is 1. And similarly, the second to last remainder, well, we know it has to be greater than the last remainder. And since this thing is at least 1, that means this thing must be at least 2. Which is the third Fibonacci number. And now that we have this start, we can look at this equation. Oopsies. And what does this tell us? It tells us that Rn minus 2, if we ignore the Q, then we get a greater than or equal to Rn minus 1 plus Rn. And this thing we have already said is greater than or equal to F2 plus F3, which is F4. And similarly, Rn minus 3 is greater than or equal to Rn minus 2 plus Rn minus 1, which is greater than or equal to F3 plus F4, which is F5. And if we work our way all the way back up the tower, what we find in the end is that B is greater than or equal to R2 plus R3. And if you do some details to figure out exactly how the, how the indexes are working, you will find that this is Fn plus Fn minus 1, which is Fn plus 1. That's at least if I have chosen the indexes correctly. I hope I have. But the point is that, okay, what is the result of all this? Let me step back for a second. So we supposed it takes n recursions and found that B had to be greater than or equal to the n plus first Fibonacci number. And if you remember, last time we were able to get a bound on these Fibonacci numbers. So B is greater than or equal to alpha to the n minus 1, because recall we got this bound that the nth Fibonacci number is greater than or equal to alpha to the n minus 2, where alpha is this thing. And what do we conclude from this relation? Well, we can take the log of both sides and get log B is greater than or equal to n minus 1 times log alpha. So if you remember your logarithm rules, if you have an exponent in your logarithm, you can take it and put it as a constant in front. And this, what is this essentially telling us? It's telling us that up to constants, the number of recursions is less than or equal to the logarithm of our input. So the Euclidean algorithm is O of log B to find the GCD of A and B. So what this means is that if you are using this algorithm to try and find the GCD of A and B, and you're asking how long it will take, how many operations it will take, based on the size of these inputs, then that is answered for you. It will take on the order of the logarithm of B. To be precise, that's about how many recursions it will take at a maximum.